Hello, and welcome to this example lab, which will be focused on the USBX library and the CDC class. So my purpose is to show you how to configure STM32 that it will use the USBX and will behave as a CDC class, which is basically a virtual COM port, which you can see on your PC to send and receive the data. For this, we need some hardware. In my case, I will demonstrate it on STM32C071 Nucleo board, but any STM32 with the USB connector can be fine. For this, we will need two USB cables, one for the debug and second for the USB, which we'll use to send and receive the data. For the software, I will use CubeMX to generate the code. And then I will use the VS Code with the STM32 VS Code extension for the debug and compiling the code. What we will create? We will configure the STM32 for the USBX to connect to the PC and to act as a CDC class, which is basically a virtual COM port. So you will see it as a normal COM port inside your terminal. And the behavior of the application will be very simple. I will show you how to check if you received any data from the PC, and we will simply send them back. So we will create a very simple loopback, and this is only to demonstrate how to handle the receiving and the sending of the data, which is the main purpose of this class. So I think we can start. So we will start with the CubeMX. I will open my CubeMX. My CubeMX has started, so we will create the new project. So I will start new project. I will wait for the device selector to appear. And in my case, it will be C071, but any device with the USB will do the same job. And we can open start new project. I will not send starting from the Nucleo. I'm starting from the completely empty project, so you can see what you need to set and what don't need to be changed. And first of all, we will locate the USB periphery. In this case, this is our simpler USB periphery. It's called USB. On the other devices, you can have the periphery called the USB OTG full speed or high speed, but behavior will be almost the same. So you will select the USB periphery and we select the device only. It should mark for us the pins. And only thing which I need to change here is to enable the interrupts. So we will enable the interrupts. And inside the parameters, I don't need to change in this case anything at all. But enabling only the USB, it's not enough to make the USB itself work. The issue can be the clock source, because asynchronous periphery don't have any synchronization clocks or signal. So we need to have the precise clocks, which the default clock inside the STM32 are not precise enough for the USB. But we have workaround. In this case, we can go to the RCC and there will be the CRS synchronization periphery, which allow to hook up on some existing precise signal and calibrate our internal clocks to meet USB requirements. In this case, we can select directly the USB. So your PC basically will create the time base for you, because on the USB, the PC will send periodically some messages. So we can use it to calibrate our clock. So located the CRS synchronization. In case that this periphery is not on your device, it's possible. On the older devices, we don't have it. In this case, you need to use the high-speed clock and you need to have the crystal or any external signal which will be precise enough to handle the precision. So now the USB should work itself, but we need the USB stack to handle the enumeration and the basic behavior of the USB, which our PC will expect. And for this, we use the USBX. So click on the USBX. And we enable the core system. we enable the device's full speed, the core stack for the full speed, the device controllers, which will be the interface between STM32 periphery and the USBX stack. And at the end, we will select the class, which will be the CDC ACM class. This is how the USBX named this class. In the platform, we only found here the solution that we want to select the USB. Nothing needed here. And in the USBX part, we need to do some changes. First of all, the USBX stack requires for its work some buffers, which are big enough to allow the USBX to work. In this case, we need to define it on the two places. One is we need to define the memory pool size. In this case, I will set it to the 10 kilobytes. This is one part, and then this will only create the buffer. But there is the second part which we need to tell USBX how big buffer this is. So here inside the device command init, in the device system stack size, we change it to the again 1024 multiplied by 10 to the same size. If you select too small buffer, the USBX will refuse to initialize, and you will basically get an error during the initialization. I think that the value can be maybe a little bit lower, but I'm using it as a default value. You can play with it later to see if something lower will also be accepted with the USB. What can be interesting here, it's the endpoints which will be used by our class. The USB CDC have usually 3 endpoints. One for the data which going from your device into the PC, one for the data which going from the PC into your device, and there is the one command endpoint which can be used for some service handling, and I think from some emulation of the clear to send lines. By default, it looks like this, that we have the endpoint 0, which must be always on any device and any class. We will have the endpoint 1, which is this service 1. In our case, we will not use it at all. And then we have the endpoint 2, which have the direction from your application to your PC, and then endpoint 3 from your PC into the application. This is important to know because we need to, inside our code later on, select these endpoints and the buffers for the USB periphery. So it's good to know which endpoints we are using to be sure that we select the correct buffers. And this is all, only what was needed to select these buffers. We don't need to enable anything else. We will not use any pins, any GPIOs. So we can go to the clock configuration. And inside clock configuration, only what is important to check that the USB is clocked by the 48 MHz for the full speed, and check that you're using the correct source. In our case, we're using the clock synchronization system, so the internal clocks are sufficient. In case that you're using the external HSE, it should be clocked from the external HSI or from the PLL if you have the device with the PLL. Only what I will change here is the speed of my device to make it a little bit faster. The speed of your system, it's partially important because if you select too slow speed, it's possible that you are not efficiently executing the USB stack, and your PC expect some answers in some timing windows. So if you not provide the answer fast enough, the PC have tendency, or the operating system have tendency to disconnect the device because it thinks that it's a faulty device because it's not answering in the time. Usually I think something faster than the 12 MHz is enough, but okay, here I will select the maximum one which the C0 can do. I can only name my device, so C0 072 USBX CDC. And in my case, I will select the CMake because I will use the Visual Studio Code with the CMake, and we can generate the code. My project was generated, so I will try to locate it. And you should open the Visual Studio on the place where you have this CMake lists.txt for the extensions and the CMake add-on to be able to locate the project and be able to build it. So I will open the Visual Studio. And usually the ST extension should be able to go to the files on the system and try to locate it if there is the project which he can recognize, and he should offer you that he will convert it into the Cube project. You can see that he was able to locate my project. You can click yes that you want to add it as a CMake project and the Cube project, so he will start to add the configurations and the configurations how to build your project. In case that this message will not pop up, and in case that you are 100% sure that you are on the inside this root is the CMake list.txt, you can try to force it manually, that you use the Ctrl+Shift+P, and here you will find the command STM32 Cube setup Cube project. Also, I forgot to mention to have the correct version of the extension, which I think we have the Cube extension STM32 Cube IDE for VS Code version 3, which is currently in this time of the recording is in the pre-release, so you need to switch that you want the pre-release version to have the same version as I have. So the build is done, the project was located, so I should be able to build it. I can try to build it to see if he's able, and yeah, he's building. So far, if I build it and if I run the code, it will not do anything usable. I will not do anything with the USB. I need still do some changes, so we can go to this changes. So I will make it a little bit smaller. And we can start with the changes. So first of all, I will go to the USBX and the app USBX device.c. There should be function for the initializing the USBX stack. It's called basically from the main, and here is the USBX initialization which I need for my CDC class to work. So here you don't need to change anything. You can control here if you have the correct stack size, because this is the buffer which you are giving to the USBX. And if it's not enough, you will usually return the error on some initialization returns. That usually it means that the stack here it's not enough for the USBX to properly work. But what I'm interested here, the USBX, it's using the time base, and so far we will not giving him any time base at all. So what I will do, I will here add the function to give him the proper time base. And I will give him the library time. So we will return the HAL get tick function. And this is all from this file, so I can save it. I don't need to change anything else here. In case that you want to check when your device is detected, you can use this callbacks for the attachment and remove, but I will not use those one. I will use a little bit different approach to check if my device is connected. So this is all for this file, but it's still not enough to make the USB work. One thing which I need to do, it's to start the USB itself, because so far we only calling here in main the initialization of the USBX, but we not calling the initialization of the USB. It's here already prepared, so it's here inside this function, the MX USB PCD init. Here is the initialization of the USB periphery, but it's not all what I need or what is needed. First, I need to tell him the size of my buffers for each endpoint. For this, I will do it with on this periphery. It's the HL-PCDX PMA config, which is the configuration of the buffers for the endpoints. And if you remember from the slides which I show you, we have the endpoints for the endpoint 0. So we have in and out. So this is this buffer. We have one endpoint for the service communication, which is the endpoint 1. And we have the one buffer for the in direction and one buffer for the out direction. The numbers here should correspond with the endpoint numbers. The 0 here and the 8 means if the direction is in or out. And also you need to assign the sizes of these buffers. On the full speed, the maximum size of the endpoint is usually 64 bytes. And here we adding setting the buffers in the words, which means in the one here mean 4 bytes already. And be careful, these are not directly the sizes, these are basically the increments. So the 20 here means that the size of this buffer is 20 minus 0. Here the 60 means that it's 60 minus the previous value, which you already defined, the 20. So you need to assign these values incrementally, and you cannot simply skip it. This is only for you to assign the proper values, but I think those are just fine. But this is not yet enough to start the USB. I need to do 2 more steps. One is to connect the USBX and the USB periphery because they don't know each other. So I will use this USBX function and I give him this USB periphery handle. So now the USB and USBX know about each other. And the last part, I need to start the USB periphery itself because it's not yet started. It's usually up to the user to start it when he wants or when he is ready. So I will use the HL-PCD start function to start the USB. And to make the USB working, or at least to be able to enumerate, I will do one last thing inside the main, because I'm not using any operation system, and the USB needs to have something which will periodically maintain the state machine and check if somebody asks for the request and the reply on them. So I need here to add the function which will do this for me. And I forget the one part, I need to call the initialization, sorry about that. So I need to call this initialization which we just filled, sorry. And now the function to make USB state machine working is here, the UX device stack task run. So this needs to be periodically called, and this is needed for your USB stack to handle the enumeration with the PC to see if he gets some new data and reply on this data in time. In case that you have the operating system, there is usually automatically created task inside the ThreadX, so you don't need to call it, but in standalone version you need to call periodically this function. So we can store it and we can build it. The build should be without the issues. So we will see he started building. We'll see if I made any errors. But I hope it will be okay. Seems it will be without the issues. A few more files, and we will be ready to go to start the debugging. It seems it's okay. I have the size, the usage of my memories. So we can move to the debug. I will create the debug configuration for me, and I will use the STM32 Cube ST-Link GDB server. I don't need to change anything here. I can simply save this file to not set up the configuration again and again. And I simply start to debug, check that your ST-Link is connected. And because I have only one board, it should be able to run the debug session. Seems that my memory was flashed, and yeah, he is in main. So I can simply run the debug. I can try to pause it to see that he don't end up in any error handler or something like that, but seems that he is not. And now I will search for my USB cable and I will try to connect it inside the USB connector for your application. I heard that my Windows discovered new device. So I will try to here open the device manager. Inside the device manager, we will try to locate the COM ports. I have here the one generic belonging to my PC. I have one to the ST-Link itself. And then I have this one, and this is the one which I just created. I can test it that I simply disconnect my USB connector, and this COM port should disappear. After device manager, yeah, the COM port is no more here. If I connect the USB connector, you will see it again. So at least seems that my enumeration is okay, but we want to send and receive data. If you try to send and receive something, it will not work. So we will need to add this part now. Now for this, we will move into the another file. We will now move to the file USBX device CDC ACM, which is the main file for our class. You should have here 3 callbacks. One is called when the class is activated, which is basically connected and enumerated, so you can start using the class. One is the deactivation, is the opposite, that somebody removed the device, most probably. One is the parameter change. About this I will talk a little bit later. So we will use them to first check if we are connected, and for this we create one variable, which I will call it CDC ACM. It's the pointer. We will use this to remember that we getting to remembering the instance of the connected USB. So I will put it inside the activation that I want to remember this this pointer. It will be now not null. And again, if we disconnect the device, I will set it back to the null. So now I will be able checking of this pointer to see if I'm connected or not. So we will use it for the transmit and reception to check if we are able to transmit or we are able to receive something. The third callback, the parameter change, is normally not needed in our case. In this case, it will be only needed if you want to use the CDC class really as a bridge between the COM port, which is inside your PC, the virtual one, and the physical one, which is, for example, on the STM32. So here you can check what is the parameters of your COM port, like the baud rate, like the number of the stop bits. So this will be callback where you will checking it, and in case that the user change the baud rate, this is what will notify you to change the baud rate on the physical UART. But because I don't have any physical UART here, I don't want to use it. I don't need to handle this function at all. What I want is to create the function to be able to transmit and receive. So for the transmit, I can prepare the function which will be handling the transmit. So I will call it USBD CDC ACM transmit. The parameters are quite simple. I will give him buffer. I will give him the size of this buffer which I want to send, And also I will get back how many bytes he was able to send to the PC. I need one service variable for the checking of the return parameters. And important part, I will here check if my device is connected, because I can call this function whatever I want. So I will check if the class is really present or not. If this is null or not, I will be not able to use the USB, and I will, for example, return the 1. Otherwise, I will, for example, return the 0 or whatever you want. And for the transmit, I need to create the do-while loop to see if my transmit was done correctly. And I will check the return parameter if it's already transmitted or not. So I will use it at 1. I'm checking the USBX state next, which means that the data which I give him for the transmit were already transmitted. And now the final transmit will be function UX device class CDC write RAM. As a first parameter will be the CDC ACM handle, basically. Second parameter will be my buffer. The third parameter will be the size of the bytes of the size of the buffer. And third parameter, it's how many bytes he was able to send. And of course, I need to remember the return variable of this function to see if I was able to send it or not. So I created a little bit blocking function. You can do it in the unblocking way, that you simply ask, you check the parameter, and if you discover that he was not able to send anything or he's still sending it, you will not expect that he will proceed this buffer. So this is for the sending, and we will do very similar thing for the reception. I will prepare similar looking function for the reception. I used the wrong line, so sorry about it, but it will be almost the same. It will be receive. Again, I will give him buffer for the reception, the size of this buffer, and he will reply me how many bytes he was able to receive. Because he is not forced to receive complete buffer, he can only receive the fraction of this buffer. Again, we will check if our class is enumerated and connected. And I will call the receive function, which is very similar to the one which we had here. UX device class CDC read run. The run abbreviation is for the standalone version. I believe if you're not using the standalone, it's without the run. And again, we're giving him the buffer, the handle, the buffer, the size, and how many bytes he was able to receive. So we can store it. We will most probably call it from another file. So we create the function prototype inside the header file. Like here. And this is all for the transmit and receive function. So when you want to transmit something, you can call this function. If you want to check if you receive something, you will call this function. And we can simply try it, and we can try it from the main. So to be able to do it inside the main, I will probably need to create some buffers for the transmit and receive. So I will create here some private variables. One is the buffer, so I will select the size 64 because this is currently my endpoint size, but you can select the buffer which is much bigger if you want. And I will create also two variables to inform me how many bytes I received and how many bytes he was able to send to the PC. And I can create here very simple looking structure that I will call my receive function. I will give him the buffer. This is the size of my buffer, and he will return me how many bytes he was able to receive. And I will do very simple check. I will check is received the different from the 0? Because if it's 0, I know that I didn't receive anything or anything new. If it's different from the 0, I receive at least one byte, so I can react. And we were talking to create the very simple loopback. So I will basically send these bytes back. So I will use the same buffer. I will send the number of the bytes which I received back, and I will for sure can check how many bytes I was able to send back. And of course, I need here to send or received back to 0 to be sure that I will not run here in the infinite loop of the reception and transmit. So I can save it, and we can build it and try to debug. We can build the code. I hope that now it will be a little bit shorter, but I was changing also the header file, so maybe not so much. Yeah, it was shorter. So I can try now to run the debug session. And in the meantime, I can try to open my terminal. Debug session is running. I also have my terminal. So I can run it. I can hear that he was able to enumerate new device. I will try here to check the COM number. It should be, if you remember, the 43. It was the my COM number. For the other parameters, which you usually have on the terminal, the baud rate, the bits, the stop bit, they are not used in our case at all. So it doesn't matter whatever speed you here use, because on the USB side, it's not used at all. It's really used only if you're creating physical bridge between the virtual COM port inside the PC and the physical one on the STM32 that use the USAR periphery. Then you can read those parameters and based on this set your USAR. But because I'm not using it, these parameters are for me pointless. Only important parameter is the COM port, because you need to connect to the correct COM port. The rest doesn't matter. It will not speed up your USB. I can try to send and receive something. So 1, 2, 3, 4, 9. And you can see I received it back. We can cross-check it here. I can put here the breakpoint. And I can do the transmit again. For example, only 1, 2, 3. And you see that I stopped after the reception. I should be able to cross-check the buffer. You can see that I have 1, 2, 3, and then the end of the message, the carrier return. And I received, I think, 5 characters, and I will send them back. When I press run, we should see them, that he was able to send them back. With the breakpoints and the debugging of the USB stack, be careful. During the enumeration, I will not recommend to put any breakpoint inside the main to stop the task run inside the enumeration process, because then most probably your PC will unconnect your device. But when the device is enumerated, there is usually the endpoint 0 is not much used. Also on the CDC, most probably not. So you can afford to put here the breakpoint and stop the stack during the debugging. This is only to warn you that with the USB don't like to be stopped, so you need to be careful. This is always what I recommend if somebody is playing with the USB, to have also the physical analyzer for the USB communication to see what is happening. If the issue is on the bus or it's somewhere in the stack configuration, it can also help a lot. So we were able to connect with the USB to send and receive the data. So you should be able now to create your own device and communicate with the PC. There is the one additional thing which I wanted to mention about the throughput. The direction from your PC into the device, the reception part in our case, is basically handled by the PC, and when you will be able to retrieve this data, he will send you as many data as you are able to receive when you clear this buffer. He cannot force you, like on the normal COM port, to receive the data if you are not prepared. So there will be no overflow during the reception. Is impossible on the USB. On the other side, for the transmission, the Windows is behaving for the transmit direction, for the in direction, a little bit strangely, which is not visible on the first look, and I will try to explain it. On the USB, there are usually some messages called the start of frame. On the full speed, the host will send them each 1 millisecond. So 1 millisecond here, 1 millisecond here, 1 millisecond here. And between this start of frames, he is able to ask for the data. The way how the Windows, or I think also the Linux, handling this asking for the data is, he asks for the data, and if you have any data, you can give it to him. If you give him the data which are lower than the maximum size of the endpoint, which is in our case 64, he thinks, okay, this transfer is done because he give me the less than the maximum data. I can ask after next start of frame. So basically this throughput will be 63 bytes per 1 millisecond, which is not so high throughput. And it can be created by the user because he giving him the lower size or the buffer than the host thinks. In case that he give him 64 bytes, he thinks, the transfer is not yet done. He have most probably more data, so he will start ask more frequently until you still giving him the maximum size. Until give him 0, he thinks, okay, this transfer is probably done. I will ask next start of frame again. So you can see the transmit, the bandwidth can be much bigger with this approach. So be careful on the sizes which you're giving him. It's not visible on the first look. It's aligned with the USB specification, but it's nowhere written that the Windows or your PC will behave this way. So be careful on this part. And that's all for me. I hope it was useful for you and that you will be able to create your own USB CDC device.